All right. So, welcome back, everyone. So we're going to go over more review, and then this will probably lead into drawing Lewis structures, and then we'll go into all the ways we can draw Lewis structures. Okay? Let's just put it like that. All right. So I sent all the invitations to Campus Wire, so hopefully you signed up by now. Active, you signed up. So next week, what you should focus on for the quiz anyway is your lecture notes. That's pretty much it. Okay, so anything like introduction, Lewis structures. We'll talk about like other common stuff that we talk about, like sigma pi bonds. That was on the homework too. That is stuff I could ask. So start on the homework, okay? That's your best way to review for the quizzes. And if there's any general questions about those, you can come talk to me, okay? So, quiz 1, next Thursday, which is, I don't know, the 21st, I think. And then homework 1. I'm still going to have that due next Thursday as well. Okay? And then for lab next week, I'll tell you how to prepare. So if there's any general questions, let me know. But we'll do the first workshop assignment in the discussion handout, which is the workshop manual on Canvas. Okay, but I'll point you where that is, so you know where to find it. Okay, and then today in lab we'll just do a lab safety orientation introduction, and that should only take like half the period, so we probably won't be there for the whole period. Okay, so probably your shortest day we'll have besides Thanksgiving break, I guess, for this class, right? All right. Any general questions? If students who are still on the wait list, please register. I gave those first 6 people permissions. I noticed that some people haven't registered yet, so please take care of that before the end of. Hopefully the end of this week, okay? If there's any problems, let me know, okay? All right. And please make sure you sign in because there's people on the wait list who are looking to add, okay? So make sure you secure your spot. If you don't want to secure your spot, one of the people on the wait list will, pretty sure, be more than excited to join the class, all right? Okay, but any general questions for me? No? All right, let's continue where we left off. So I believe we stopped at covalent bonding. All you really need to know about covalent bonding, those are the most common bonds in organic chemistry, organic compounds. Electrons are shared, and you have 2 types of covalent bonding, okay? And we're going to first talk about what constitutes a bond, okay? So we have sigma bonds. As the name implies, they are the stronger of the 2 bonds. okay, and a class of their own. We denote this with the sigma notation in Greek nomenclature, or Greek lettering, okay? So does anyone remember what's the difference between, say, a sigma bond and a pi bond? It has to do with the overlap. Does anyone know the difference? All right, so sigma bonds are the result of direct overlap of atomic orbitals. So it could be atomic orbitals. That's the general definition. But when we talked about hybridized, you might have heard of hybrid orbitals. That also applies too, okay? All right, so a sigma bond is pretty much any bond in a compound that has is at least a single bond, okay? So I like to say any quote-unquote single bond, okay? So, for example, let's use sulfur, and the Lewis structure, this is going to be sulfur. All right, so hydrogen sulfide. All right, sulfur has 2 lone pairs on it because it's like oxygen, right? Likes 2 lone pairs, likes 2 bonds. Okay, so here we can say that sulfur will use one of its orbitals here, and hydrogen will overlap like this, and you'll form a bond there, okay? So if you can't see that, I basically drew 2 arrows up and down, all right? So this here, we can say there's overlap between sulfur's 2p orbital and hydrogen's 1s orbital. So we have an SH bond here. So here's an SH bond. It's composed of sulfur's 2p orbital and hydrogen's s orbital, like that. All right, so that's a sigma bond. There's actually 2 of them here. There's another one right here. Like that. So there's 2 single bonds for sulfur hydrogen bond. Okay? So when they're overlapped directly on the same axis, so you see how they're kind of on the same axis, the orbitals are in contact. That is called direct overlap. So here is direct overlap. Okay? All right. So what I want you to take away, you don't have to draw this diagram, okay? You just need to pinpoint like, oh, what's a sigma bond, what's a pi bond. This is usually how it's taught though, okay? That's how overlap occurs. And that's why single bonds are the strongest. They're the most difficult to break. When you have a double or triple bond, usually you break the pi bond first because it's weaker, okay? But are there any questions about sigma bonds there? This is just an example. It's for any compound that has a single bond, so like methane, CH4, or water has a sigma bond between oxygen and hydrogen. All right, let's talk about pi bonds now. So I'll use a different color. But are there any questions about sigma bonds? Any clarifications? No? All right. So pi bonds have the Greek letter pi in it, okay? So the difference here is not side-by-side overlap. It's not direct overlap. It's side-by-side. Okay? Of orbitals. So it's through space. Where single bonds, or or sigma bonds, they had overlap directly. Here it's side by side, okay? So you can know something's a pi bond if a bond between two atoms is any double bond okay, that counts as one pi bond. And then any triple bond as well. Okay, so a triple bond actually counts. So a triple bond, there's two additional bonds there. So it's not going to be one pi bond, it's going to be two. Okay, so two pi bonds right there. Okay, so let me give you some examples of this. So, the simplest alkene is ethene here. All right, you know where we find this. So, anyone know polyethylene terephthalate? That is PET plastic. That's commonly found in water bottles. Not the water bottles you have here, but the ones you can find like Costco, Safeway, maybe not Safeway out here, but Nugget, stuff like that. Those bottles are made of this molecule, ethene, and with another molecule called terephthalic acid. And that forms a polymer, and you can make a wide range of materials with it, okay? But the flexibility comes in with how this double bond can be kind of manipulated, okay? So, this is like saying we could draw this like so. All right, now I drew all the sigma bonds. All right, where does the pi bond come from? Anyone remember?
Double bond with carbon.
Yeah, so what orbital is that bond using from the carbon atoms? Yeah, thank you. You're exactly right. So we could draw these p orbitals like this. Okay, and this electron here indicates that there's a bond here. And remember, in the p orbital, the electron can be in the top lobe or the bottom lobe. It doesn't matter. So the bond is actually below and above and below the bonding region between carbon atoms. So that's why you have such, the double bond so much stronger than the single bond. There's forces of attraction above and below these p orbitals, okay? So that's side-by-side overlap. We call it parallel overlap because it's perpendicular to this line here. Okay? All right, so this bond here, so this interaction here is our double bond. All right. Now it's a little bit tricky to draw, but for a triple bond, you're just going to have an additional p orbital in between the carbon atoms. Okay? So let's say we have here's an alkyne. Alkynes have use in chemistry. They're not as prevalent as alkenes, but they're still important in like pharmaceuticals. Okay? So here is my carbon backbone. Now I'm going to have two sets of p orbitals. One over here. All right, now I have to show this in different colors because the next set is hard to draw. But imagine you have another set of p orbitals that are perpendicular to these p orbitals. So it's going to look like the p orbitals are kind of, let's see, pointer is. They're kind of going through this direction right here, okay? But I'll draw it for you so it's easier to see. It's like this. So try your best to draw it like here, and it's going to kind of stick out like that. And this one's going to stick out like that. And the p orbitals are going to go in front and behind the carbon-carbon axis. That's the second set of p orbitals, and that's going to be our triple bond there, okay? So this thing right here is our triple bond. So the most important thing here, you've probably seen these drawings before, is not to reproduce these drawings. That's something we ask of you in Gen Chem, okay? What I am expecting is that you can look at a molecule and say, okay, this is sp hybridized, sp2 hybridized, sp3 hybridized. But before we could get into that, we have to talk about overlap, and that's why we talked here. Identifying sigma and pi bonds, because we'll refer to those terms a lot, just for describing structure, okay? Are there any questions on this example? Okay, so notice how I'm using examples in organic. If it was in Gen Chem, I would have used like carbon monoxide, nitrogen, or carbon dioxide to illustrate these examples. Okay, no questions? All right, let's go. Yes?
So just to clarify, the triple bond joint nature, would that be an sp3?
No. So, all right, let's go over that. So, if I was talking about this carbon right here, what hybridization would that be?
Sp.
Not sp. So which one is for pointer? sp, sp2, or sp3? Sp. No, not sp. That's linear. sp2, right. So this is sp2. Okay, and that's because this carbon atom, what geometry is it? I think I heard it under someone's breath. Trigonal planar. But if we look at this carbon atom, what's its geometry? Is it planar? Is it tetrahedral? So you only don't need to know chem. Linear, tetrahedral, and then trigonal planar. And then for water and like oxygen and nitrogen, bent trigonal pyramidal. But what is this one? This carbon right here. Is it linear, trigonal planar, or tetrahedral? So remember, tetrahedral, we need 4 groups around the carbon. 3 for trigonal planar. What about for 2? Linear. And you could think, the easy way to think about it is this molecule, right? What kind of shape does it look like? A line, a triangle, or a tetrahedron? Or a pyramid, let's say pyramid. Looks like a line, right? It's like straight over here. Looks like a line. So that'll be linear. So this carbon here is sp hybridized. All right. But I'll go over that again too. So, all right. Any other questions? No? All right. All right, so let's go over now polar bonds. All right. So for covalent bonds, it's either polar covalent or non-polar covalent. What does polar mean? If we say something's polar, what does that mean? In terms of a molecule? Yeah, good. So there's a region within the molecule that's partially positive, partially negative, okay? So to identify polar bonds, you need to identify certain elements in the bond, okay? So polar bonds are usually given to molecules that mainly have bonds of this type, mainly XH and XC bonds. Okay. Well, when I list these bonds out, what does X usually mean in this case? Element, right? But it has to be an element with relatively large what property? A certain property. You probably learned about the elements where they participate in bonding. They don't share electrons easily, right? What kind of property quantified that? It starts with the letter E. Yeah, electronegativity. Good. All right. So X here would be something, X is oxygen, nitrogen, chlorine, or fluorine. For here, we're going to say electronegative elements. So those are the elements with the highest electronegativity, okay? So if you need help remembering the order of electronegativity, I have a mnemonic I like to use. So I'm going to do right here, most. So EN stands for electronegative, and here's least. All right, so you want to tell me the most electronegative element? Fluorine, good. So F, and then there's a mnemonic that's known for it. It's called Fonkelbrisk. ONCLBRSCNH. All right. So I'll kind of put this in a little box here. All right. So the reason why I said any of these more electronegative elements attached to carbon and hydrogen, which are the least electronegative elements, those will have the largest difference in electronegativity. So those are the most polar bonds. Okay? So an application of this is if you have a non-stick pan, frying pan, it has what we call polyfluorinated alkanes, okay? And when you have a lot of fluorine atoms attached to carbon, they don't like to stick to anything. So you have a non-stick pan, right? Nothing sticks to it, not even water, right? It just all forms off. And that's because the electronegative fluorine atoms are pretty much repelling everything away, okay? They don't want no more electrons, they don't want anything coming near it. So that's why they're called non-stick. Basically, nothing adheres to them, okay? So that's an application of this property in a nutshell, okay? So any compound you see with OH bond, CO, CF, they're going to be particularly polar, okay? Well, let me take that back. Not CF, okay? CF is a little special. There should be a caveat there. Put a star there. Except CF. But don't worry too much about that. You won't see a lot of CF bonds in this class. It's kind of specialized, okay? So anything with XH or XC bonds, you can safely assume you're going to have the most polar bonds there, okay? What about nonpolar? So those are polar bonds. What do you think are nonpolar bonds here? So elements that have, bonds that have elements of low electronegativity, right? So they're pretty much bonds with what two elements? Carbon, carbon, and carbon, hydrogen. Why do you think alkanes are so nonpolar? They only have CC bonds and CH bonds, right? So bonds with low electronegativity atoms, okay, and they are, the most common are CH bonds and CC bonds, okay. So we could probably think of a polar compound. What's one example of a polar compound? Maybe we use it every day. H2O, water, yep. So example here would be an H-O bond, water. Right, very polar. And then a non-polar bond could be any alkane, right? So you could do something like, methane, ethane. Maybe let's just do propane. See, only C bonds and CH bonds. Like that. Okay. All right. Any other questions about polar and non-polar bonds? Okay. So I just want to see our understanding of these things, because we'll have to be able to draw these kind of structures and understand where they come from. Okay. All right. All right. Switch gears. So that was we kind of talked about valence bond theory right there. Atomic orbitals overlapping, forming bonds, and you have two classifications: ionic bonding, covalent bonding. Covalent bonding, electrons are shared equally, or they're not shared equally, hence the names nonpolar and polar. Okay? All right. So I might talk, if you take 18B as well, I will have to talk about this theory, so I might as well talk about it now. Okay? All right. So let's talk about molecular orbital theory. I'm just going to mention it briefly. Okay? This theory, as you might have heard about it, it's particularly an advanced theory, so we don't go into it in great lengths here, unless you take an advanced inorganic or organic course. But I'm just going to give you the bare details here, okay? So, has anyone heard of molecular orbital theory? Maybe in Gen Chem? Any ideas? I don't know, because Dr. Dykes taught it, I think she mentioned it, but I'm not sure if she actually went over the diagram. Anyway, I will just go over it briefly, okay? But does anyone know what I'm talking about? Like, what's the difference between molecular orbitals and atomic orbitals? Anyone? Okay. No, it's an advanced theory, so I'm just wondering. Okay. So we say this is a advanced theory of bonding. Okay. So what happens here is, all right, what's highest level math people taking? Has anyone taken linear algebra? No? Okay. So in linear algebra, you can do mathematical operations where you take these orbitals and you spit out new ones. Okay. So what you're doing here is atomic orbitals. S and P usually here, okay, are combined to give new orbitals called molecular orbitals. So I can remember when we learned about hybrid orbitals, Dr. Dykes probably had like a bag of S and P orbitals. She told you to mix them, and she gave you two new ones. Kind of the same idea for molecular orbitals. Instead of hybrid orbitals, you're forming orbitals that occupy the whole space around the molecule. Okay? So they give us molecular orbitals that spread out or over the whole molecule. Okay? And the most common example I'll show you is H2. All right. So you have an H here, here's the 1s, and here's this hydrogen's 1s. So when you mix these orbitals, you're going to get two molecular orbitals that are higher in energy and lower in energy, okay? So this, we denote them as sigma 1s, sigma 1s star. All right? So how many electrons are in the 1s orbital for hydrogen? For just one hydrogen atom? Yeah, just one, right? So that's 1s1. So let's put it right here and right here, okay? So what this diagram is telling you, that look at the hydrogen, the 1s orbital for each atom is in the middle, right? So it's perfectly like that by itself. But when it forms a molecule, we can say, all right, in order to form a molecule, it must form an orbital that lowers its energy, right? Chemical reactions don't happen by itself if you don't have a lowering of energy of the system, right? Like gasoline burns is because you're releasing a lot of energy, the molecule is now more stable. So this process won't happen if you don't have a net lowering of the energy. And so for that to happen, you must form orbitals. The resulting product must have orbitals that are lower in energy, okay? So you're going to have an orbital like that, okay? So this is one of the MOs. And then you're going to have an orbital higher in energy, like this, okay? So you're going to have two types of orbitals, right? The orbital that promotes bonding is called the bonding molecular orbital. So this here is our bonding MO, okay? So this is the orbital that favors bonding. Now this orbital here, if that one's bonding, what do you think the higher energy one is called? Yeah, anti-bonding. If you populate this orbital, or if there are electrons in this orbital, it will favor the opposite of bonding. It will favor separation. Okay, so this is anti-bonding. Thank you. So this is actually, it favors bond breaking. So basically, if this orbital is filled, it will actually negate the effects of being in a bonding MO. Okay, so if both of these orbitals are filled equally, no bond will occur between the two elements. Okay, but now we have to fill up the diagram. Since we only have two electrons outside, how many should we fill in the middle? Two. Thank you. Like that. So since both of these electrons are now lower in energy, the H2 molecule forms. Okay? So H2 here forms. All right, so that's why H2 exists. So we use this to kind of explain things that Vesper theory, valence bond theory fail to predict. And that's why MO theory is now well understood. And that's the better model now for bonding. So there's several modes of bonding here. MO theory is one of them. It's one of the most advanced, and it has support from experimentation. That's why it's often taught now. Okay? All right, any questions about that? Just think about, like, these are the methods of our understanding of bonding in chemistry. And now we're going to use this understanding and see how it applies to reactivity. Okay?
Do you always go the lower one first?
Oh, no, just assume they're equal. I didn't draw the scale. Okay. Yeah. You don't have to, don't worry, you don't have to, like, draw one of these things. I'm just explaining, like, the theory behind it. Yeah. But I'll tell you right now, it's not always the same. But it is the same when you have both of the same atom on either side. All right, so that's MO. Any questions? No? Yes.
So, are we gonna have to do this? Like, I know for Gen Chem 2, like, we had to draw the whole diagram.
Oh, okay.
I'm wondering if we do that in OChem.
No. This is kind of just like a review of Gen Chem for now. But no, we will probably just talk about this one time. And I don't expect you to draw it. Okay? All right, but any other questions? It's a good question. All right. Trust me, ML theory gets a lot trickier, especially when you're talking about compounds with more than 2 or 3 atoms. So it gets, especially with metals. I don't know if you guys talked about that in 1B, but there's a lot of ML diagrams too in metal complexes. All right, so now let's talk about Lewis structures. Okay. The heart of chemistry. So in organic, we'll teach you the many ways to draw Lewis structures. You'll have to be able to draw a Lewis structure with kind of no fuss. What I mean by that is you can draw them on exam or quiz very quickly without any hesitation, right? And when you're in Gen Chem, you learned about it. You kind of we're just starting out, and you drew Lewis structures, calculated the valence electrons, distributed the electrons and the bonds. In organic, you should be able to do that without having to consult that process and do that fairly accurately. Okay, we'll have a lot of practice this week, today. I'll start talking about it, and then next week in lab we'll have an activity where we just draw structures. Okay, so Lewis structures, named after the chemist who proposed this idea of Lewis structures. Okay. And yeah, I wonder, I still think, historically, I don't think Lewis ever won a Nobel Prize, which is baffling to me. Okay? It's crazy. But anyway, so each line, so when you draw lines between atoms in the Lewis structure, right? Each line represents how many electrons? Right. And are those electrons shared or unshared? Shared, right? They're between 2 atoms. Very good. Okay? So if each line is 2 shared electrons, then each double line, so each, okay. Sorry, that doesn't make sense in English. So 2 lines is how many electrons?
4.
Thank you. And then what about a triple bond? How many electrons is that? 6. Does anyone know what the name for this thing is? This math notation? I'm not sure. All right, it's not important. All right, so those are shared electrons, right? How do we represent unshared electrons? Say, for example, oxygen doesn't use all its electrons to bond, right? What are those called? Lone pairs, right. Good. So we can have unshared electrons. Those are lone pairs. Okay. And those are represented as 2 dots. Usually, it doesn't matter if it's written horizontally or vertically, or you can place them however you want, as long as they're around the atom. And they should be right next to each other, around the atom too. I'll give you some examples later. All right, and then sometimes we have single electrons, usually unshared. Okay? And it's represented with a single dot. So these compounds, when you have compounds like this, they are called radicals. And they are called radicals for one, they are unusual to see, and they can be fairly reactive. Okay. All right. So let's give some examples of this. All right, we have methane. So here are examples of everything is shared. Methane, CH4, ethene, and then ethine, acetylene. Scratch that. Okay. So all of those are shared, right? Now let's talk about unshared electrons. So here's an example of unshared. Okay. So we have an amine, which is amines kind of one, they smell like ammonia, kind of fish-like too. These higher order amines, like methylamine, ethylamine, they're byproducts of like biological processes, and they're treated through the digestive system for some animals, fish and like, mainly fish and aquatic wildlife. And they have these type of compounds with nitrogen in it, so that's what they mean. Okay. We also have oxygen-based compounds. Most common one that we metabolize, ethanol, through both food, diet, regulation. And then we can also have halogens. So these are the three most common type of organic compounds where you have an atom with lone pairs, oxygen, nitrogen, and then the most common one for halogens is chlorine-based compounds, but bromine and iodine also exist. Fluorine does exist, but it has special properties. You see it too. So you never see like acetine. Okay. So the only halogens we have to worry about fluorine, chlorine, bromine, and iodine. But I'll go over that a little bit more later. All right. Are any questions about these structures here? No? All right. So we also have an example of a radical. So this would be unshared. So here's a radical one. Nitric oxide. Okay, so this is nitric oxide. So the importance of this, so this is a radical. It has an unpaired electron. So see here, nitrogen doesn't have an octet, right? So that makes it kind of reactive. But this molecule, in actuality, is quite stable. And the reason why it's stable is because of its bond order, or the double bond character you see between the two atoms. That radical kind of helps make that bond very stable, okay? And that's why this compound is commonly encountered as a biological signaling molecule. So during metabolism, physiology, this molecule has been implicated in numerous processes for signaling, so it's biologically relevant. Okay? All right. So you might be wondering, how do we know that nitrogen always has 3 bonds, oxygen has 2 bonds, halogens only have 1 bond? Well, there's some bonding patterns that we'll go over. Okay? But are any questions right now? How we drew the structures? Any questions? No? All right. Did everyone sign in to attendance? I saw some late. Okay. Where's the attendance sheet? I passed it somewhere. It must be circling around. Can you pass it up front? Yeah. Thank you.
I need to sign.
Oh, okay, yeah. If you came in late, you could sign at the end. I won't mark you down. All right, bonding patterns. So one thing I've picked up is that when I was learning OChem, my instructor didn't really tell me the bonding patterns between the different functional groups. So I didn't know that oxygen always had 2 bonds. I kind of just had to infer that by my own study. So I'll give you that information, okay? So let's look at the bonding patterns. So let's write the elements. Boron family, carbon family, nitrogen family, oxygen family, halogen. All right. Anyone else? Okay. So, boron has how many valence electrons? 3. So here let's put, so we have 3 here. So this will be like valence electrons. Okay. How about carbon? 4. Then nitrogen 5. Oxygen 6. Halogen 7. Okay. So there's a couple boron. Don't worry about boron yet. We'll get to that. Okay. So if carbon doesn't have an octet, so this is a bond to carbon, this is a bond to carbon, this is a bond to carbon. If it's missing 1 bond, what charge does it have? Might not have thought about this. Does anyone have a guess? +1. So plus. No octet. Okay. So now let's use this information. What does nitrogen look like if it has a positive charge? 1, 2, 3, 4, positive charge. Okay? So if carbon has 3 bonds, positive charge, nitrogen has 4 bonds, oxygen will have, well, it might be hard to see here, but oxygen with 3 bonds and 1 lone pair is a positive charge. All right. So it looks like we're going from 3, 4, 3. How about halogen? I don't think halogen 4, that doesn't make sense. So if it's going in natural order, I would guess 2. All right, and chlorine here, let's use chlorine as our example. +1. And if we refer back to formal charge, if we count all the electrons around chlorine here, it has 6 around it. 1, 2, 3, 4. Well, can you guys even see? It has 4 electrons from lone pairs. And then in any organic compound, chlorine will share electrons in bonds, right? So from each bond, it actually has 1 electron associated with it. So that's why when we calculate formal charge, it's going to be 7 minus 6, which is +1. But I'll go over that later. We're going to go over formal charge later, okay? So if you have any questions about that, try to hold off from asking them until then, all right? So, but halogens, we usually don't see this type of plus charge here, only in like intermediates, like during the course of the reaction. But as a stable compound, halogens usually only have 1 bond, all right? Okay, so now let's talk about when are they neutral, okay? So, what's a neutral boron compound? How many bonds do you think a neutral boron compound will have? 3, yeah. Boron is an exception to the octet rule, so it has no octet here. All right, how about carbon? How many bonds for a neutral carbon?
4.
Yeah, thank you. Very good. All right, nitrogen is going to be 3, right? And the rest is a lone pair. How about oxygen? What do you think oxygen is? 2, right? Use water as an example. Like that, okay? All right, how about halogen, say chlorine? 1, right. So after you go from boron, it goes in order 4, 3, 2, 1. All right. Now, so the important, you'll see these types of bonding patterns. That's why I introduced it. Now we're going to see patterns where it's negatively charged. So boron, to get a negative charge, you have to take a lone pair and form a bond with it. So boron will have 4 bonds now. That's negative charge here. All right, carbon's a little different. Can we add any more bonds to carbon? No. So you actually have to take that bond and make it a lone pair. Okay, so carbon anion is like this. Okay. So what do you think nitrogen will look like? Well, it can't form another bond because it'll be positive, right? So we're going to take nitrogen and take that one of its bond and turn it into what? Yeah, you got it, lone pair, like this. So when you have nitrogen in this form, it has a special name. It's called an amide. But that is also the name for a functional group with nitrogen. Okay, so I wish there was a better term for them, but that's what they're called, okay? But you could just call this a nitrogen anion if you so prefer. All right, oxygen. What does hydroxide look like? We have O. Instead of hydroxide, this is called this oxide. So we're going to have a negative charge. So instead of additional bond here, it's going to be a lone pair. Negative charge like that. All right. Okay. How about chlorine? What would the negative charge for that look like? So when you think of chloride, how many electrons are on chloride? 7 is chlorine. How about chloride? If it became an anion. Yeah, it'll be 8. Like that. All right. So those are some of the bonding patterns you'll see, and you'll have to be able to draw. Okay. So for example, carbon has a lone pair on it, negative charge. Carbon with just 3 bonds, no lone pairs, positive charge. That's called a carbocation. We'll go over those terms throughout this course. Okay. And they do explain some of the reactivities here, but these are the common reactive intermediates you'll see too in this class. All right. Any questions about the bonding patterns? I know it's a lot, but just know what they look like in their positive form, neutral form, and negative form. Now you don't necessarily have to memorize these things. You can kind of see it through practice by working through problems too. And that's my goal. Okay, so let's talk about let's talk about formal charges for a bit, and then we'll take a little break. Okay, so do you guys remember how to calculate formal charge? You'll have to be able to do that pretty quickly in this class. If you're having trouble with that, I can help you. I'm going to teach you a trick, okay? Well, I'm just telling you, when you're drawing structures, you have to be able to tell me, am I missing a positive charge or negative charge? If you miss those charges and it's a structure type question, I'll take like 0.5 each time that occurs. okay? It just bugged me. I have to, okay? At Davis, they're even more strict. They'll take a point, okay? But no, formal charge is important. It tells us, where the charge is in the molecule, how electrons are being accounted for. It's more like an accounting system, pretty much. Like, where does the electron go in the structure? All right. So formal charges. So if there is a non-zero formal charge, you must show it explicitly on the structure. Always include them. Okay. So there is a formula you probably learned about formal charge. I kind of edit it a bit. Maybe they do the same thing. So here are the steps. Okay. So to determine formal charge, the first thing you should do is draw a circle around the atom. So this is a circle method, okay? So say I have, so I'm not writing out the bonds to carbon here because I'm not trying to find the formal charge for carbon. All right, so let's say we're looking at oxygen, right? So I'm going to draw a circle around oxygen. Okay. All right, has anyone seen this method before? It's called the circle method or the arc method. All right, so basically, you're going to count the number of dots and lines in the circle. Okay, so what's the total number there in this circle? Good, 6. Remember that, okay? So you're going to count number of dots and lines in the circle. All right, so let's put that. This is step 1. I forgot to write that. All right, step 2, you're going to subtract the number you just determined from the valence, the number of valence electrons for that atom on the periodic table. Okay? So subtract count from number of valence of atom. So here you would look at periodic table. All right, so for oxygen, how many valence electrons does it have? 6. So here, that's your number of valence electrons. All right. And from the circle, we counted 6 electrons, right? So these will be electrons around oxygen, okay? All right, when we do that, what's the value here? 0. And that makes sense, right? Because we don't have a charge associated with oxygen, so its charge is 0. So you could do that for any atom in question, okay? So if you want to test this out, you could do it for the rest of this molecule. So this molecule looks like this. This is methanol. You could do it for each oxygen, each carbon atom, and each hydrogen atom if you wanted to. And if you do this method, the charge should always be 0 because there's no charge associated with methanol. Okay? But let's do some other examples. Does anyone have any questions, though, first about how we calculate the charge. So if you do it this way, it's really easy to do it for each atom in your head, in my opinion. But otherwise, you have to follow that formula, which is valence electrons minus number of electrons in bonds divided by 2 plus electrons in lone pairs. You have to remember that formula. Okay? But with this, a little simpler. Okay? So let's try it for medoxide. So let's use a different molecule here. So this is medoxide, a strong base. Oops, sorry, I got that wrong. All right, so we're trying to figure out the charge here for oxygen right here. All right, so see if you can calculate the formal charge for this one. Oxygen still has 6 valence electrons, but I think there's more than 6 around oxygen in the circle. So what's the formal charge? All right, how many electrons are in the circle? 7. So our formal charge should be? -1. And that makes sense, right? We just saw on the other page, oxygen with 3 lone pairs, 1 bond to it, should have a -1 charge. We just verified here, it has a negative charge right there. All right, now I'll do it for this example. H3C, OH, H. All right, what's the formal charge on this one? So we're going to still circle oxygen. But notice now, unlike the previous 2 examples, it has now an additional bond. All right, 6. In this case, 6 minus what? 5. Positive 1. There you go. And we saw that on our chart there, that oxygen with 3 bonds in a lone pair, that's the positive form of oxygen in this series. All right. Okay, so let's pause it there for a few minutes. 10-minute break. Need water break, bathroom, just take a breather, reset your brain, and we'll come back and talk about some other forms here. Hey, what's up?
Somebody yesterday emailed you to sign that form. It was taking like 20 minutes.
Yeah, what happened? Did you get it?
So that was a petition so that I got approved for 20 units, but they're not that. So when I tried to register last night, they wouldn't.
So it's still going through, I think?
Yeah, still going through. Yeah.
All right. Well, you know, when we find out, you know?
I'm gonna go. So tomorrow after work, during my lunch break, so around
Okay.
like 1, I'm gonna go check it out.
Where you have to go?
I'm gonna go to Marysville campus.
Oh,
I live in Yuba City.
Oh, okay. Yeah,
So
it's quite a drive from there, man.
I know. Yeah. So
Okay.
I'll get it all checked out over there.
Is there a reason why you want to take it here and not Yuba City?
I just had a bad experience with the professor over there.
Oh, have you taken this class before?
No, I took a
Previous class.
Previous class with the professor over
Okay.
there.
Yeah, we know about that. So
Yeah.
we understand. Yeah.
Yeah.
Okay.
And all my other classes are taking Calc 2, I'm taking Bio.
Are they here or up there?
Here.
Okay.
Yeah. So
Sounds
I
good.
got Pretty packed schedule, so that's why I'm
Yeah, man. 20 years. Do you have enough time, man? I just worried about that.
I have
You think
time.
so?
Yeah.
Okay.
I will have time, yeah.
Do you work?
I do work, yeah.
Oh man. Busy dude.
I took 14 units over the summer too, so I was able to manage it.
Damn. You doing 2 majors something? Double major?
Just one major.
Wow,
I'm
okay.
just planning to graduate, so.
Yeah, you just want to get in and just get done, right?
So I want to
Move
do the
on.
medical field, yeah. So
Oh yeah,
it takes a lot
yeah.
of years, so I want to save. some.
Right. I mean, just the whole process there probably was 7 years just to get through. Good luck, man. Okay. Yeah, thanks for letting me know.
But yeah, 1.12 was pretty good. Just like drawing chemical structures.
Oh, yeah.
I do not remember that. I do remember that in like something. Like that little like a test.
I'm so bad at every single question that had that.
Oh, like the lines and then things in the
See,
function.
that, I remember that so much when I first took Orgo, and I was like, oh my god, I was like, I actually know this. You know I have another part here. Oh, this is confirmed.
I was so funny because my boyfriend yesterday asked me like how many carbon turn methane? I'm like 4. And it's like 4 hydrogens or something.
Oh,
And then that's what he said. I'm like, how does he know? It's like one thing. Yeah. It's like everyone gets upset all year.
Where I was like trying to get the original mom to. It's sad.
Is that like the net color?
This guy's brown. Their ability.
Oh, I have that too.
How do you actually do?
I don't know.
I don't know.
They do the same thing. I'll play around with it tonight, see if I can get it. Now we can go to the
All right. Hopefully, my break was helpful. All right. So let's just pick back up where we left off. All right. In this class, we will see carbon, oxygen, halogens, nitrogens in specific ways. So I thought I would give you like a little breakdown of what these different fragments could look like. Okay, so In this class, you will see carbon as so this will be for neutral carbon. So this is a carbocation. A carb anion. This is a carbon radical. It's also neutral, but the only difference here is that it doesn't have 4 bonds. Okay? Charged or no octet. So those are how you can see carbon in organic compounds. Okay, one with double bond, triple bond, single bond, and it has a charge. Either it doesn't have that 4th bond, or it's a radical. Okay, so that's what carbon will look like. All right, how about oxygen? So let's look at oxygen now. All right, either oxygen has 2 bonds to something, usually carbon, or a common form of oxygen is in the form of this form. That's called a carbonyl or carbonyl group. Okay, very important functional group. So this is what it will look like as a neutral compound. If it has a negative charge, it will look like this most of the time. Okay, or you have a positive charge. There's 2 forms oxygen will take. This is called an oxonium ion because it's positively charged. And this one is, man, I'm forgetting what this one's called, but I think this one's also oxonium ion, but it's from a double bonded oxygen. So those are pretty common too. Okay, so that's for oxygen. Not as many flavors as carbon, but nonetheless, you'll see oxygen like this. So you have to know if it's neutral, negative charge, positive, and that can give you some information about how it reacts in a reaction. So you shouldn't really think about memorizing these things, but think about, in terms of reactivity, positive and negative charge, how they attract each other, and how does they react in the end. All right, nitrogen is next. Has as many forms as carbon, but that's because nitrogen is also very prevalent. Okay, so let me just scroll up a bit. So oxygen. Now let's write for nitrogen. So nitrogen, the fully neutral form, 3 bonds to nitrogen, or nitrogen and a double bond, lone pair, or nitrogen with just a lone pair and a triple bond. Okay, so all these forms are neutral. And then for charged species, so here you can have it as charged. So I just put charged down here. Okay. Positive charge for nitrogen. So it looks like an ammonium type compound with 4 bonds. Or nitrogen with a double bond and 2 single bonds, still positively charged. Or nitrogen with a triple bond or 4 bonds around it, positively charged still. Okay. And then you also have a negative charge. Nitrogen can also appear like this. Okay, so those are the main forms of nitrogens you'll see in this class. Okay? All right. The last one we had to go over. Which group is missing? Halogens. How do the halogens behave? Okay? Well, halogens is pretty simple. They typically behave in the only manner you might expect as neutral, as we've seen them before. Because we never really seen a halogen with more than 2 bonds, right? Unless it's a central atom. Where carbon's not the central atom, right? That's pretty rare. So, let me screw up. Is everyone done with oxygen? All good? Let's go to nitrogen. All right. So now let's do halogens. All right. So you have fluorine, chlorine, bromine, iodine. So iodine, so I would say based on this order, the 2 central ones are the most common halogens. Iodine has special uses, but it's also pretty common. But by far, chlorine, bromine, they are the ones that have been used for ages in this field. Fluorine has specialized uses too. So most of the examples I'll show you will probably have chlorine and bromine. Okay. All right. So those are the major forms. Neutral, right? These are the neutral forms. But of these halogens, they can also participate in 2 bonds. But the most common one that does this is bromine. So you will see something like this. Bromine is forming a triangle like this. So this is one example where bromine, or the halogens in general, will be positively charged. Okay? So positive charge here. All right, so that structure looks weird, probably just by looking at it. It's like a triangle with bromine in it, but there has been implications that this does form. Okay, so this does exist. Okay, so those are all the forms you'll see, most of the common atoms and elements in this class. All right, are any questions so far? No? All right. Yeah.
Have ever been negative?
Yeah, negative? Yes, it will. It'll actually be negative, but it'll just be by itself. Yeah. So you might see halogens negative too, but or as salts, right? For example, sodium chloride. Here, chlorine is negative, right? We will see that, yes. But I guess the patterns here I was talking about more when it's bonded to carbon. You'll never see a halogen that's negatively charged with carbon. Yeah. But that's a good question. Any other questions? Okay. So now let's go into drawing structures. I'm going to go over the 3 types. Okay. And this is something we'll have practice with next week. In lecture, I'll probably talk a little bit more on Tuesday when I refer to resin structures. All right? So, So when we draw in organic structures, there are 3 ways we draw them. Okay. So the first way is called Kikuchi structures. A more common name for them are Lewis structures. Okay, they are named after the guy who developed or kind of postulated this idea. So these are what we generically know as Lewis structures. They include all atoms drawn out and lone pairs on atoms, heteroatoms, and all the bonds are drawn at 90-degree angles, right angles. This, irregardless of what the actual shape is. So those are Kikuchi structures. So, for example, if you have ethanol, you have 2 carbon atoms linked here, oxygen, hydrogen. Like that. Okay, so look, all the atoms are drawn at 90 degrees. All the elements are shown, and the lone pairs are included. Okay, so let's draw a little more complicated structures, and you'll see why this way of writing organic structures has some limitations. Which the first one is, I don't know, does oxygen have 180-degree bond angles? No, right? No. So that's the first thing. Next thing we'll see is that you can run out of space when drawing these structures, especially for very branched and more complicated carbon structures. All right, so see here, I have this oxygen here. But in order to fill, I have to make some bonds longer than others, or else they'll kind of clash with other atoms in the structure. Like so, okay? And if you have to draw out all the atoms for, say, compounds with more than 20 atoms, it becomes cumbersome, okay? All right, so that's a organic compound, has an oxygen and a chlorine atom in it. Now this one. Oh my bad guys, sorry. Back up. This was supposed to be a nitrogen. All right, so this compound right here has both an acid group and an amino group. Does anyone know what kind of group of compounds that is called? You have your carbohydrates, you have your lipids, your nucleic acids. What's the one for proteins called? What kind of biological compound? Do we know? Amino acid, yes. So this is actually amino acid, but it's not the ones we usually know because these are beta amino acids. The nitrogen here is on, the nitrogen right there is on the second carbon from the C double bond O. All right? Our amino acids are alpha. They are at this carbon. That's where the nitrogen will be branched off of. Well, actually, I think it's still amino acid. But anyway, all right, we have different classes of amino acids, is what I want to say. So that's a polyfunctional compound, okay? It does a variety of different things. Okay? All right. Good. Okay. So these compounds, when we draw them out, they can become tiring, especially if you have to draw like a really big structure. Okay? So another way we represent organic compounds is using what we call condensed formulas. Has anyone heard of condensed formulas? All right. So condensed formulas, they're like the molecular formulas you probably heard about, except you don't condense everything into the individual elements like C5H10 O2 or something. You actually condense it based on how the structure is written. Okay. So I would say here, this is the way to represent structure as elemental symbols. And the order here of atoms suggests the connectivity. So basically, the order it's written, that suggests how it's drawn or how it's ordered in connection, okay? So for example, if we took this, if we took the previous examples right here, right? If we look at these, all these, so let's look at all those and try to draw condensed structures. Okay, so let's do the first one. So I can abbreviate each carbon atom based on how many hydrogens they have. So if I go from left to right, left to right, the first one would be CH3. Okay, CH3, CH2. All right. And what would I write for the last one? What am I missing here? OH. So looking at the OH, right? Right here. So see here, I didn't condense the carbons. I put them side by side. So that illustrates how it's connected, right? First, I have a CH3 group on the left, bonded to the CH2 group. And lastly, it's bonded to the O and then the H. All right, are any questions on, let's start with this. Are there any questions on how I did that? Okay, so let's do the second one. All right, so the beauty of this is you can read it from right to left or left to right. There's no really any default order, but it's usually left to right, okay? Let's do the second one. First, we start out with what? Cl, good. All right, CH2. Boom, all right. We have a problem. Do we go up or do we go to the side there? Okay, so usually you read these things, you can't go like all loopy-loop here. You have to go straight in a line, okay? So if anything is coming outward, branching off from the top or bottom, you have to put that in parentheses, okay? So this one will go to CH, all right, parentheses, all right. What's the order going, starting from the oxygen? So O, and then what? Yeah, you're right, CH3. Good. Okay, very good. And then lastly, CH3 on the other side. Okay, so there's a default order. So if we didn't have these kind of guidelines here, people would do condensed structures. That wouldn't make sense because it'll all be randomized. You can easily just say Cl, CH2, CH, parentheses CH3 and then say CH3. So there has to be some, there has to be some default reading order. So either left to right, or right to left. Don't go from left to up or right to up. Doesn't make sense. Okay? All right, are there any questions about the parentheses?
Yeah.
Yes.
Can you explain when we use them again? Is it like when we go up?
Right, so see, let's look at this. See the structure here? If we go left to right, correct, we notice that the OCH3 is kind of altering, it's going on an alternate path. So we call those branching chains. So anything on branching chains, you put in parentheses. Yeah. Yes?
If you have a branch and chain that's going both up and down, or on the same element, would you put them in separate parentheses, or?
Let's see. That's a good question. Okay. That's an interesting question. No, I think you would actually have to draw one coming out like this. Because if you do double parentheses, it's kind of hard to picture like from which carbon it might be coming from. There might be some ambiguity. So if it's coming from both, my recommendation is you don't do parentheses and you actually put the bonds up and down. I can give you an example. So let's do another example here where we have, so say we have, okay, let's see, Cl I'm not going to draw these all out just because I'm illustrating a point. Say you have something like this. Okay. From Alexa's point right here. What if they're both branching out like that? So to handle this one, you actually shouldn't use parentheses. It actually makes you more confused. So what you should do here is ClCH2, C, and I would just draw it OCH3 like this, OCH3 like that, and then put CH3 right there. Okay, that's the clearest way you could do it. That's actually how I taught it last semester when I taught 2B, and we went over that. But yes, good question because so honestly, I never really thought of that before. Or maybe I didn't do enough examples where that was possible. These things are possible. It doesn't have to be the same group. They can be different. CH3, CH2, CH3. Doesn't matter. You do get situations like this. All right. Any other questions about the use of parentheses? We'll see them a lot, so when we see something new, I'll try to expand on it. Okay. Now let's do the last example. This was just for this example when they're both substituted. Now let's do the last one. All right. So there's also a time where you might see it like this, okay? So if you read left to right, let's look at the last example, the one to the far right, CH3NH. You might read it like, wait, that doesn't say CH3 first. That says H3 then C. It doesn't matter. You can write it either way. So I'm going to write it this way. H3C. That's just a backwards CH3, okay? That's fine too. Okay. Then we have NH. Then what's next? CH2, good. All right. How do I abbreviate the C, the carb? So that's the last group there. That's called carboxylic acid. So there's a few ways you can do it. In OChem, there's usually only one way we write it. All right. So in Gen Chem, you might write acetic acid, the acid part, as CO2H. And here we expand it. So it's typically written like this. COOH. All right. Okay. So next week we'll see a variety of different functional groups, and I'll show you how to draw them. Okay. We won't have time to go over all of them right now. All right. Any questions about condensed formulas? These are sometimes how you will see structures on exams for reactions. You'll see a reaction, and then over the arrow, it might just say the condensed formula. Okay. So you have to be able to interpret both. All right. So let's wrap things up here with bond line. You might know this formula, this structure formula, or this structure drawing as skeletal structures. You guys remember that? All right. So skeletal structures, that's just a more descriptive name. The formal name is called bond line. So we call it bond line, and that's because all you see in these structures are bonds represented as connective lines, okay? So let's do the first example, ethanol, okay? So if we go back, let's use this as our kind of our template here, ethanol. All right, how would I represent that as a skeletal structure? So bond line, let me just, so someone has it? Boom, boom. All right, so let's take some notes on this. Only CC and CX bonds shown. And for bond line, you technically don't have to show the lone pairs. Yeah, you don't. But I do anyway, okay? So you should still show lone pairs because that helps you know that they're there. So if there's lone pairs on heteroatoms, you should show it. If there's lone pairs on carbon, you should show it, okay? Etc. Okay? But here, only CC and CX bonds are shown. You technically don't even show bonds to hydrogen, and you don't show hydrogen atoms on carbon. So let me just make let's make a little point here. H atoms on carbon are implicit. Does everyone know what I mean by that? They are, yeah, go ahead. Anyone understand what I mean by implicit? It sounds like the word implied, right? So they are there, we just don't show them. So you should know that they are there. Okay? Heteroatoms. So like oxygen, nitrogen, phosphorus, sulfur, halogens, fluorine, etc. are shown. Okay? And then each point on the drawing represents a carbon atom. And each carbon atom will have enough hydrogens to form an octet. Okay? So each carbon has enough hydrogens. Okay? They are implicit on carbon to form octet. So, how many hydrogens are right here? 2. So there's 2 H's, okay? How about right here at the end? 3 H's. Good. Okay? You only show the hydrogens on heteroatoms. Oxygen, nitrogen are the most common. Yeah, they're pretty much the only ones that will have it. All right, so let's use that example and try this one up here. All right, so this one, Well, let's just use this formula we've written up there as our guide. So we have a Cl right here. Okay, so Cl is right there. CH2. Guys, for heteroatoms, if you don't put lone pairs, that's fine. I'm just showing you that for now, so you know that they're there, okay? All right. So that's the second example. So see here, chlorine, CH2. So I just drew it down this time, even though I drew it up in the other structure. And that's because I started to zigzag in a particular way. It doesn't matter, okay? Because if you just flip the molecule over, you'll see it as the same structure, all right? Okay, so look right here. We have a new type of carbon now. How many hydrogens are right here? One hydrogen, good. All right, let's do the last one. This amino acid looking structure. We have CH3, so we look at this structure. There's a CH3 first. So CH3, and then we do N here. So you don't have to show the bond to H. Just have to associate it with it. Okay, you don't have to draw it out. All right, then we have CH2. And then here, you usually write it like this. Double bond O. The C is implied. OH right here. All right, that's skeletal structure. Oh, I forgot some lone pairs. Just for now, okay? So that's bond line for this last structure we drew from Kukui to condensed, not bond line. Okay, are there any questions? All right, we'll have more practice, don't worry, but the homework will have you draw some of these skeletal structures. That's how you go from condensed to bond line, okay? All right, that'll be it for today. I'll see you in the lab in like 10 minutes. If you have any questions, feel free to come by.